Okay, you must be careful. You cannot put this just in front because. But like this is okay.
Is that yours?
Yeah, that is mine. What is which one?
I mean the web.
No. This is borrowed from Martin.
Yeah, we should order one.
Yeah. Okay. I'm actually not good at this technical stuff. So. Okay. So can I start? I mean, it's not much. Okay. And also we are low on time, so I better do faster. I thought we had more time, but okay. So the goal of this is just to outline a few basic topics that I can suggest to some or scholarship student or master student or PhD student or whatever. Okay. And I have given. Yeah. What is there something? Okay. So I have given 2 talks. So talk 1, talk 2. Yeah, and I do not want to repeat now. This is the reason why. What's the problem?
Have to reflect it.
No. That is okay. This is correctly reflected here. There is something wrong with the camera over there. I don't know what. So I have given 2 talks. Okay. And there is also okay, there is a material on Slack for both of them, and then there is a third material which I put today. And that material is not for the talk that I'm giving now, but I have already in preparation put this because I may give some third talk in, I don't know, maybe in 1 week or 2 weeks, depending on how we schedule this. Yes.
Too difficult to read. I mean, the handwriting is.
Yeah. Okay. Okay. You have to interrupt me. Okay. Yeah. My writing is so. This is why I speak, right? I don't only write, but I also speak. So here are some very basic topics that I can suggest. So the first thing that I talked about, can you read like this? Talk 1. So the was some kind of complexity theory, and there are okay. For example, there is the not recognition. So the not recognition problem. There is also for example the invariant computation. So I explain what are invariants and what are okay. So this is like how do we recognize them. And Donghyun already started investigating about this. So he knows now some things actually which I did not know. And I cannot offer too much assistance on this because I'm not expert on this complexity theory thing. But this is something that one can think about. Okay. Well, you already checked the literature. Okay, you know some things that I did not know. So okay.
My recognition is something like this diagram, this sequence diagram is actually represents.
Yes.
Yeah. I think this problem has been kind of trivially solved.
Well, this is algorithmically in a theoretical sense, but not in a practical sense.
Right.
Yeah. So okay, I mean, this is the one class of questions that one can consider. As I said, I'm not too much expert on that, so I don't want to say. Want to say more about this. Then the other thing that I outlined in talk 2 was the let me call this the move tool. Okay, which so transform one diagram into a table diagram. And then I said so in a Notscape. And so that it needs to be fixed. Now, as far okay, I talked to Martin, and Martin said basically this is not really a new algorithmical stuff. This is why this is more something for master student or okay for master students. But for example, one can try to extend this to links. Okay. All this functionality works so far only when I have one circle. Okay. So when you have things like that, okay, but you can have also things like this when you have two circles. Okay? And now there is a notation designed for that. Okay. And you can try to implement the same moves also for links, and that would be already somewhat more substantial to algorithmical contribution, because you have to think about some things. Okay. And so this will be a more substantial project, which would be more, I mean, as far as I understand what are the criteria for from Martin, this would be more something for a PhD. I mean, this whole move recognition tool. So these moves do not work only for nodes. You can have them also for links. Okay? Yes, write the programming, but write a correct program. Okay, so I emphasize very much on the correctness, because all the time I'm plagued with errors, not only of myself but also of other people. Okay, so this be another topic that one can investigate about. Then I will talk about this in talk 3. Yeah, so the next time I will talk something about the not polynomial computation. And so there are several problems with that. So first to fix the bugs in Netscape. This is easy. I write here easy in the sense that I already have programs which are, I mean, I don't want to say 100% bug free, but extensively tested and with no problems. Okay, so how to integrate them into Netscape? This will be just an easy task. Basically, you have to modify some of the internal procedures. So this would not be too difficult to do that. Okay, but and then modify my programs. I will talk about this in the next talk. I will talk about how to calculate braid index. I defined in the first talk what is the braid index. I'm trying to make some braid index table. This is something that I'm doing right now. And okay, this would be a little bit a piece of work to do. How to modify these programs to be efficient for some particular type of nodes. Okay, so this is the smallest number of strings that you need to represent a node. So right, so you have something like this, right? Okay, and I say the braid index of the node is the minimum of n, such that there exists a braid in Bn with the closure is given being the node. Right, I defined this in the first lecture. If you look at it, you will see. I didn't talk about it too much, but okay. So I mean, there is more to knot theory than I can fit into 2 lectures. So this is a basic invariant which you can consider when you deal with. Okay, and then trying to calculate this, and this requires some efficient modifications of this program. Yes, but I need to do it better. I have some very difficult examples, and I need something to be done better. But I do not want to tamper around with the program anymore. I have been working on this for a couple of months. Okay, and I do not want to. So this is some for somebody else. Okay, I can give this to some student to work. Okay, this is still okay, this is moderately difficult. You can do this to make some braid index table. And then there are other things, for example, parallel computation. I don't know if anybody is interested in this kind of thing, because the processes they run over a very long time, and it is better to share CPUs. So well, for now I can use one CPU for one computation, but okay, one can think about this kind of thing.
I heard it has many CPUs.
Yes, but I cannot use many CPUs for one computation. I can compute several nodes on several CPUs, but not one node on several CPUs. Okay, and so this leads then to examples where I need to calculate to a very long time, and then now you have to think about how to cut the time. So one thing that you can do is you do not calculate the whole polynomial. You try to calculate only what you need for that. Okay? But another thing that you can try to do is that. And so this will allow you to compute more in less time when you can use multiple CPUs. It's not okay. It's a long-term project. It's not okay. not a huge priority, but one can think about it. Okay, and then there are also some. I will talk about some skin braid hybrid method. But okay, this is now very okay long-term project. So and then the last topic that came to my mind in introducing what one could do is with matrices. You know, there are, I didn't talk too much about it, but there are many ways to associate matrices to nodes. So algebra is totally related to that. One thing that I introduced was Burrow. I wrote down the Burrow representation of the braid group, and then I said I'm going to say something about it. And in talk 3, I will now say what the Burrow representation has to do with that. But this is one thing that I did not have in mind here. There are other matrices that one can associate to nodes. So the one is the Goerritz matrix. Okay, and you can use this. So and now you can use this Goerritz matrix to you interested in the signature. So Goerritz matrix is a symmetric matrix, and the signature. So this means this is the number of positive eigenvalues minus the number of negative eigenvalues. This is symmetric. It's obviously the diagonalizable over the reals. Okay. The signature of this matrix gives you an invariant, so you can use this to calculate some invariant of the node. Okay. So Goerritz matrix by the signature, or the other thing that you can do is you can calculate torsion numbers. So this is, I wonder if anybody has been doing this here. So what does this mean? So this is an integer matrix. Okay, so you have, let's say G is in M. I don't know what notation you use. Maybe okay, the standard notation which I use is something like that. Okay, so you have here rows. Okay, and then you can consider Zn factored by Z span of the rows. Okay, so this is a lattice in Zn or in Rn. Okay, it's cofinite. I should say that, let's say the determinant of this is when you have a knot, then the determinant is always odd. So okay, this is regular. So this means that okay, this is a finite group. Okay, so this means it is a finite abelian group. So this is like ZD1 plus ZD2 plus etc. And D1 is divided by D2 is divided by D3, etc. So by classification theorem of finite abelian groups. And I mean, okay, and this is not an invariant. Okay, the Goerritz matrix is not an invariant, but this is an invariant. So the group that is determined by that is an invariant. So and these things are called torsion numbers. Okay, and I'm looking for some fast algorithm to calculate this. This matrix will in general be large. So let's say 30 by 30 times 30. Okay. If I want to calculate for some serious examples, okay? But it will be sparse. Okay? And I'm looking for how to calculate this quickly. Okay, and the problem is without overflows. So I have an algorithm for that, okay, which is okay, but the algorithm is stupid. But still, if I use integer, okay, if I use the class integer for the matrix entries, this works comparatively okay in speed. but it produces overflows, and this is sensitive to overflows. When you get an overflow during this process, then the result is okay, is destroyed, so it's useless. So you have to take care of overflows. But if I then I made myself another class of overflow-free integers. So, for example, you can, when you have one integer, you can make a class of two integers. So, when one integer goes until 2 to the power 32, then two integers will go until 2 to the power 64.
You made the class yourself?
Yes. So okay. Yes, I know, but I did this in 2005 when I had no idea about that I'm going to do some computation or something, whatever. No, actually not in 2005, in 1998 or okay. So anyway, I made myself a class to avoid this overflow, and not just two integers, because when I get to 2 to the 64, I have the problem again. So I made a completely new class which does its own memory management. So an integer is an array of shorts, and then I can allocate and release memory according to as I like. Okay, this then avoids the problem of overflows, but then it gets too slow. Okay? So so for example, I take some, I don't know, Z65 plus Z65 in order to recognize this with integer. It takes half a second. Okay, and if I use my own class, which is overflow free, then it takes about 10 minutes, which is about 10,000 times slow. Okay, then I'm looking for some more efficient algorithm, for example. Okay, so what one could do is maybe one could try first with integers, but always look for overflows. And if you encounter an overflow, you throw your integer away. Then you try with two integers. I mean, and this doesn't work, and then you try with this at the end. So probably could be one solution. Okay, but something like that. Okay, would interest. But I'm interested also in algorithms. How can you get these numbers quickly? Okay, without too much risk of overflow, and you have a sparse matrix. The determinant can be still pretty large. So that may not be a very trivial problem. So you have Gödel, you have Görlitz matrix, you have also Seifert matrix. You'll find this even in Netscape, from which you also can calculate these signatures. And then if you want to use, or we can try to use then I mean real or complex numbers. So with complex coefficients, you can get then the Tristram-Levin signatures computed, and so these are some applications that one could try to use real matrices for computing signatures, or some not invariants. Okay, so this is basically as far as I want to say. How am I with my time? I'm okay. I think I shouldn't say too much more. So I hope that maybe in I don't know, next week or next week we can schedule another talk in which I explain about the not polynomial computation and what I'm doing. So then I can introduce some of these problems in more detail. But okay, these are some topics that I had in mind that one could think about, and I could try to advise somebody.